Welcome. Welcome, everyone. Feel free to take a seat. We do have some available up towards the front here. Welcome and thank you for being here tonight to support UC San Diego graduate students. My name's Tamara Shops. I'm the Assistant Director of the Assistant Dean of Graduate Strategic Initiatives here at UC San Diego's Graduate Division. And this year I've had the honor of working with the Grad Slam program, which is a UC-wide public speaking competition featuring 3-minute research talks delivered by graduate students. As most of you in this room know, graduate students spend many years conducting research, whether it be in the lab, in the performance hall, or out in the field. And they spend countless hours writing their theses and dissertations. And the goal for many is to use this new knowledge to find solutions to problems in real life. But how do they share their research with the world? And how do they share those research with those outside of their disciplines? Did you know that there's over 50,000 graduate students in the UC system? Think about that, 50,000 graduate students. There's about 8,000 graduate students here on our campus. And collectively, these 50,000 master's and PhD students are a force for innovation, and they're often generating the new ideas that keep California and our nation at the forefront. However, only a very small percentage participate in Grad Slam. We estimate it's around 1%. So the students you're seeing tonight are in that 1%. Being able to clearly and succinctly communicate the science and methodology behind research, as well as the potential impact research has on one's field and on the world, is incredibly important. And now in its 6th year at UC San Diego, Grad Slam teaches vital communication skills and also cultivates resiliency in our graduate students. And the Grad Division is proud to continue the sponsorship of this program. To the student participants and to the judges tonight, it takes courage to stand in front of your peers, mentors, family, and a panel of judges to talk about complex and nuanced research in just 3 minutes. And it also takes courage for our staff, our alumni, our community supporters to judge those students and to provide them with very critical, helpful feedback. And so I just want to thank you all and recognize you for your work tonight and for your work for students over the past couple of months. To campus partners and volunteers, special thanks to Katie Brecht. Is she here? I feel like I saw her. So Katie Brecht is our partner in the Center for Student Involvement Communication Leadership, who works with our students and coaches them and helps them refine their speeches as we go through this program. And she's been a fantastic partner for a number of years now, and I just wanted to thank her for giving her time and her talents to this program. We're very appreciative of her. And also shout out to my Grad Division staff and student workers. Thank you for being here tonight to support this program and for volunteering your time. I really appreciate all of your help over the last couple of months as we worked collectively to put this together. Woo! And finally, this year we assembled a cross-campus committee that worked to build partnerships with divisions and departments on enhancing this program. So thanks to all those who served on the cross-campus committee for Grad Slam and for promoting this event through your social networks and within the division and departments that you work in. Get social. So hashtag Grad Slam is what we're using tonight. Feel free to tag at UCSD Grad Life in any of your Instagram or Twitter posts. And again, the more active we are in the social media, the more people get to hear the messages of our amazing students. And we also have a live feed going. So if any of your colleagues are unable to join us in person, feel free to invite them to the live feed. So once the judges are finished deliberating, we will do an award ceremony. And so the finalists are each getting $500 for advancing to this part of the competition. The campus champion will be awarded $5,000. The first runner-up or second place is $3,000, and the second runner-up or third place is $1,500. So just to know that there's some skin in the game tonight, and these students are very motivated to do their best. In terms of logistics, each speaker will be introduced by our MC. The timing will start once a speaker engages the audience or starts speaking, and the target time is 3 minutes. Each speaker's official time will be announced at the conclusion of their talk, and we have timekeepers up front here if you want to raise your hands. Yay, thank you. Thank you, timekeepers. The MC will engage briefly with each speaker after their talk is concluded so that the judges can finish scoring. Please refrain from asking any questions. The only person who is able to do that is the MC. And if you would all take a moment to silence your cell phones, we definitely don't want accidental disruption for any of our contestants. Now it's my pleasure to introduce this evening's Master of Ceremonies, Interim Dean of the Graduate Division, Dr. Paul Yu. Dr. Yu is a distinguished professor of electrical and computer engineering and joined the Graduate Division in September 2018. He's been a member of the faculty since 1983, and his research focuses on the development of optoelectronic and electronic devices that enhance the performance of fiber optic networks. His work on advanced semiconductor materials and components have brought about major advancements in high data rates for digital fiber optic transmission, as well as wide bandwidth analog fiber optic transmission. And yes, I practiced that out loud a few times. As you might imagine, Dr. Yu is thrilled to be here this evening and is eager to hear from our graduate students about their exciting research. So please join me in welcoming to the stage our MC, Interim Dean Paul Yu.
Thank you very much, Tamara. It's my distinct pleasure and honor to be here to welcome all of you. You're so anticipating, excited, and just like I was a year ago. I was so excited, so they asked me to be the MC tonight. I actually was one of the judge last year, so some of you might still remember that. So it is really an exciting event. It started 6 years ago by Kim Barrett, the dean at the time. Let's have a hand for her. Yeah. So it is now a tradition at UC San Diego that every year we'll gather together today and to celebrate, and then we have one of the final student finalists will go up to Sacramento, right? Sacramento, right? To San Francisco, yes, to do the final competitions with 9 other contestants from other UC campus. It's very exciting, okay? So, but on the other hand, they practice so hard, and I'm sure that you'll see the performance, and you will be amazed how good they are, okay? So without further ado, I'd actually like to ask the judge of panels to introduce themselves first. Yeah.
Do I have to stand? Yep. I don't want to. Hi, I'm Leslie Carver. I am a professor in psychology in the Human Developmental Sciences program, and I'm also provost at Thurgood Marshall College.
I'm Bradley Fikes, the biotech reporter at the San Diego Union Tribune, and I'm supposed to give a fact about myself, interesting fact, and I am a fan of echidnas, if you know those strange creatures from Australia.
Hi, Jared Hamas, 2 degrees from UCSD, and I'm the proud treasurer of the Alumni Board, and it's a privilege to be here tonight.
Hello, I'm David Resilian, alum 09 and 11, and I'm a recruiter, and I did not know we had to say something interesting. I'll just leave now since everybody just laughed.
My name is Allison Saterland. I serve as the Vice Chancellor of Student Affairs. And in a shout out to all the partners and spouses, the first 9 years of my 21-year marriage, my partner was a grad student. So shout out to all of you that love our grad students.
So without further ado, let's have the first finalist, Emily Piers, to come up here to give her presentation. She's a student from Biological Sciences, and presentation title is The War and Peace of Cheese.
Right now, growing on and inside of you are millions of microbes. These microbes grow together in diverse communities, which we call microbiomes. Microbiomes are like tiny neighborhoods made up of bacteria and fungi. These neighborhoods exist almost everywhere on Earth, including the human body, where they can impact your immune system and even your mental health. We're starting to understand a lot about microbiomes and why they're so important, but one thing we don't know a lot about is how do organisms in these communities interact with their neighbors. The human microbiome is like a big city, teeming with diverse types of microbes. Just like it's hard for you to get to know your neighbors in a big city, it's challenging for scientists like me to understand connections between organisms in these complicated systems. Instead, I've turned to a simpler community, more like a small country town. This community comes from the rind of cheese. Cheese is actually an edible ecosystem made up of bacterial and fungal members. Rather than thousands of species, there are more like 10. This makes it a great model for us to understand more complicated systems. In my research, I study how bacteria and fungi interact with their neighbors. Sometimes you have a great neighbor who's willing to bring you a cup of sugar when you're running low. And in this case, you might love your neighborhood and stay there for years. On the other hand, you could have an awful neighbor who plays loud music at all hours of the night and keeps you awake. And in this case, you might want to move out after a couple of months. These same types of interactions take place on cheese, where organisms can either stimulate or inhibit their neighbors. Here, I'm showing an example of a bad neighbor that I found on cheese. This yellow bacteria is not able to grow anywhere close to the white fungus. What makes this fungus such a bad neighbor? One possible answer is that this fungus is producing an antibiotic, or something that kills bacteria. Fungi are known to produce a range of antibiotic compounds. For example, penicillin was originally isolated from a fungus. Finding a potential antibiotic on cheese was really exciting because antibiotic resistance is one of the major public health challenges of our time. Each year in the US, 2 million people get an antibiotic-resistant infection and 23,000 die. It's therefore crucial that we find novel antibiotics, and cheese could represent a previously untapped source of these. Although the original purpose of my research was to try to understand the basic principles of how bacteria and fungi interact in communities, this basic research has led me to potentially finding a novel antibiotic on cheese that kills major disease-causing organisms like E. coli. Here on the left, I'm showing you healthy E. coli cells. On the right, you see E. coli cells that are being killed by the antibiotic I've isolated from a cheese fungus. These cells become swollen and eventually die. I'm in the process of characterizing this antibiotic as a potentially novel compound that could be used in the future to treat human disease. Hopefully today, I've convinced you that microbiomes matter, that we can use cheese to study them, and that these findings are not just relevant to cheese, but can provide public health solutions. Thank you.
Well, thank you, Emily. Okay, all right. So I have to go up here too. So, thank you very much, Emily.
Thank you.
Thank you for a wonderful presentation that teach us about the human microbiome and also cheese.
Cheese, yeah, exactly.
So we just have a few questions for you. What is your favorite food and why?
Well, I mean, obviously mac and cheese is a great choice. But
yes.
I'm also
Anything
can't
else
beat that.
beyond that?
I also love cake. I really like baking, and so cake is one of my, my favorite
Wonderful.
foods.
Yeah. So beyond food, what is something fun on your bucket list?
So something that I've always wanted to do is go swimming with otters. I love animals, and there's actually a sanctuary nearby where you can go and swim with the otters. So I think that would be totally amazing.
Thank you. And what is your favorite sport for vacation?
My favorite spot for vacation? I would have to say probably Switzerland. I did a study abroad when I was doing my master's degree there, and I loved it. I'm also a rock climber, so they have lots of great climbing opportunities and great cheese, as you know. So.
Great. Thank you. Thank you very much. Yeah. Let's give her. Yeah. And, thank you. Thank you. Yeah. All right. Our next student finalist is Pauline Chung from Chemistry and Biochemistry. And the title of her talk is Making Renewable Fuel from Solar Energy. Let's welcome Pauline. Yeah.
What's the biggest challenge facing renewable energy today? Energy production, efficiency, is energy storage. Take solar energy as an example. In California, solar panels at midday of sunny days generate so much electricity that we had to shut down some of them to avoid damaging the power grids. Of course, we don't want to waste the sunlight, so the next step is to store solar energy as chemical energy in a process called artificial photosynthesis. Similar to plants converting solar energy and carbon dioxide to carbohydrates, which are their form of fuel, artificial photosynthesis uses electricity generated by solar panels to produce different chemical fuels. These fuels, such as gasoline and diesel, are superior form of energy storage compared to the best batteries we have today, because they can hold 10 to 100 times more energy for the same weight of folium. Therefore, in my PhD study, I am searching for catalytic systems to make renewable chemical fuels from electrical energy and carbon dioxide. Here's my approach. I surveyed several catalysts made from cheap and abundant metals, such as manganese, iron, cobalt, and nickel. They are some of the top catalysts in the world for artificial photosynthesis. And just like the enzymes used in photosynthesis, they must receive electrons, in this case, from the electrode, to convert carbon dioxide to fuel precursors like carbon monoxide here. To best make use of the electricity generated by solar panels, the catalysts are fixed on the electrode surface so that the electrons can go directly to them to drive reactions. The catalysts, as shown in the red dots, are carefully embedded into a large network on the electrode surface, represented by the gray crosses there. The network allows the catalyst to express their best catalytic performance while staying in place on the electrode surface. When the assembled electrodes are connected to the source of electricity, streams of bubbles are coupled to other chemical processes to produce chemical fuels. We really can emulate photosynthesis. We are on the right track to catalytic systems that produce renewable fuels. So, what's the potential application? Imagine if we hooked up millions of solar panels to these artificial photosynthetic systems, converting solar energy to tons of chemical fuels, and then use these fuels to power our cities. In this way, we could make renewable fuels from solar energy. Thank you.
Thank you very much.
Thank you.
Pauline. So thank you for engaging the speech on the artificial photosynthesis and connect it to direct conversion from
Yes.
solar energy to chemical fuel that can be
Yes.
supplied us 24 hours a day.
Yes.
I like to ask you, so you're passionate about this research. What is the favorite thing that you do during your spare time, which you have, if you have?
Yes. In my 5 years of grad school here, I spent quite a few time learning different dances on campus, such as Argentine tango, tap dance, some jacks, and ballet workout. Yes.
That's great. So many dances you've been practicing. What is the hardest to perform or to learn?
The hardest to learn is the jazz, because it actually requires a lot of physical strength. Yes, it's challenging for me.
Okay. Well, from your bio, you're also interested to do hang gliding one of these days.
Yes.
Can you tell us more about this item?
I believe there are several spots near campus we can do hang gliding, and I really want to do that before I graduate, and I heard from people that it's not very expensive, so I want to do it.
Okay, thank you. Is there something that you'd like to tell us that, that we do not usually know from your biography?
I have embedded a hidden joke in my 3-minute speech that people may not realize it, so yes. So I did this gesture, and if you've seen some Chinese martial art movie, it actually means respect and gratitude. So people may not realize it, right?
Okay, thank you very much, Pauline.
Thank you.
So our next finalist is Julian Chris Mendes, and from Theater and Dance, and her presentation is Theater as Immersive Imitations. Okay, thank you.
Thank you so much.
That's very good.
Walking down a dark hallway. A thick curtain is pulled back to reveal a woman in a 1940s overcoat. She reaches out her hand to you. Will you follow her? Enter stage right my research. I study and create site-specific immersive performance to deepen the relationship, the empathic relationship between audience and performer. What do these words even mean? Site-specific is a performance whose story is related in some way to the location where it is being performed. And immersive has to do with creating a 360-degree environment that supports the story. This work is hyper-local. My collaborators and I excavate local history and myth to surround the audience with resurrected stories. Behind me are research images and the path the audience will walk in an upcoming project entitled Calafia at Liberty, which is happening at the Old Naval Training Center in Point Loma. As the audience moves through time, they are going to follow historian Edward Everett Hale as he seeks for the real person behind the myth of Queen Calafia, whom he believed our great state is named after. By accessing, by sourcing local narratives and presenting them in the place where they originate, I can give audience members access to their local history. As opposed to traditional theater, where the audience is separate, in some darkness, and usually silent. This mode of being worked when the audience needed space to have emotion. However, theater is losing ground to augmented and virtual reality that are espousing entertainment instead of human connection. I'm breaking the fourth wall, inviting the audience to participate in a world of theatrical possibility. So when the audience steps into history, they are interacting one-on-one with the performer. This way of interacting is actively practicing empathy. We believe that this project and this form allow audience members to practice and witness new perspectives other than their own. And we believe that doing so will allow them to take agency in their own lives. Thank you.
Thank you very much, Ariana. So we are thankful for the wonderful presentation about the theater and your upcoming production run in the Liberty Station.
Yes, it's in October. It's
October.
coming.
Okay,
Part of the
remember,
WOW
October.
Festival.
Okay.
Yeah.
And I would like to learn something about yourself,
Yes.
about you. So tell us something about what's on your bucket list.
My bucket list is rather odd. I am a big believer in history, as we know, and I'm really interested in river jousting. And there's a river jousting festival where jousters on boats run at each other. And so there are rowers and there are jousters, and it takes place in this little town of Sète in France.
Wow.
That's my bucket list.
Okay, sounds like you like traveling.
I
what
do.
would be your
do.
most favorite destination for travel to?
My favorite, that's a tough one. I don't remember what I put on the form. But I'd say let's go generally France. I'll do generally France. Yeah.
Okay, good, good. Yeah, and tell us about someone that have a major impact in your life.
Absolutely. So my grandmother, who yesterday was actually the anniversary of her passing, she taught me a lot about treating everyone with what she called shampoo de cariño, which is a shampoo of kindness, and that you should be infesting the world with kindness.
Thank you very much.
Thank you so much.
Next, we have Angela Nicholson from Biological Sciences to present RNA regulation, the tail wagging the dogma.
Inside each one of your cells, millions of particles are constantly bustling with activity. All of this activity is organized by a molecule called RNA, shown here by these yellow dots. Each piece of RNA is an individual written message, which your genome uses to transmit information out into your working cell. When your cell synthesizes this RNA, it first makes the main message portion. After that, it creates a tail at a predetermined long length. Traditionally, it's been thought that this tail provided protection for the main message, so long was viewed as better. And this was assumed to be the end of the story. So it got written down in a textbook in this way. RNAs have long tails. And sometimes, once something's written down in a textbook, it doesn't get questioned anymore. But sometimes, you find something totally unexpected in your research. My lab has recently discovered that while RNAs might start out their life like this, they wind up with a myriad of tail sizes, and that actually short tails are the most common. But why would your cell bother to make a tail long to begin with just to shorten it up later on? By following these short-tailed RNAs, I've discovered that they actually play a very specific role in signaling to the cell that this particular message should be communicated quickly and effectively. By allowing for long tails on some RNAs and short tails on others, tail length can now be a key part of differentiating each message, being specific to what the cell needs. This finding turns the textbook dogma on its head. Now, I'm talking about a very small molecule and even smaller changes in this tail region, but these findings implicate tail length as a vital part of the message. For an example of how important this is, I want to talk about Fragile X syndrome, which is the major cause of intellectual disability. It's recently been discovered that patients with Fragile X have RNAs with different tail sizes than those who are not affected. As you'll remember, the prevailing view has been that, tails are long and they have no effect on how each message is communicated. So how could they be involved in a disease? Based on my work, we now know that tail length can have drastic effects on development. So working to understand how tails are misregulated in Fragile X could lead to some really important new treatments. This seemingly tiny change on a tiny molecule can affect how the entire human body is functioning. This is just one example of how my research can give us a new lens to reevaluate some very complicated diseases. On top of the scientific implications, this work speaks to the importance of reevaluating long-held beliefs in any field. Scientists once thought that the tail of an RNA was just a passive bystander in regards to how each message was communicated. Turns out, it's more a case of the tail wagging the dog. Staying open and curious in our research could lead to some really big breakthroughs in health in the coming decade. Thank you.
Thank you for telling us your research on RNA regulation and also the implication of the tail links to different disease. This is very exciting.
Yes.
So we'd like to learn more about you. Okay, so you have been doing some work for so long. What are the most impactful person in your life so far in this study?
One of the most impactful people, particularly in regards to this, was one of my professors at my undergrad university. I went to a pretty small undergrad that didn't have much of a science research program, and he was one of the people that really encouraged me to apply for internships and to get a lot more outside lab experience, and encouraged me to apply for my PhD. So he was very instrumental in even down to the nitty-gritty of helping me with applications and things like that.
Good. Sounds like you have a very good mentor.
Yeah.
So speaking of teaching, there's something that you can tell us more about what you like to teach your cat to do?
Ooh, yes. I have a cat, and I really like to teach her to try to catch bugs, because I don't want to kill them. So I've taken to, if I see like some flying thing, I'll pick her up and bring her over there. And she'll be really excited because she loves flying things, and she kills them and eats them.
Okay, what's something that most people don't know about you?
That most people don't know about me.
I feel like this is a game of remembering what you wrote on this form. I think what I wrote was that I used to do theater actually before my science life. One year I played both a 12-year-old boy and mind you, I was a full-grown woman at this time. A 12-year-old boy and a stripper in a different play in the same year.
Very good. So one last question.
Okay.
What's your favorite destination for travel, for leisure?
Oh, for traveling?
Yes.
I really want to go to Niagara Falls. My friends Jim and Pam had some wedding photos from there that were really beautiful, so I really want to try to get there.
I've been there. It's gorgeous.
Yeah.
So I hope you can go there very soon. Thank you, Angela. Yes. Next is Wiley Peacock, some chemistry and biochemistry, and his presentation entitled "Hero Thrombin Save Lives with Blood Clots."
Right now, at this very moment, our bodies are literally tearing themselves apart. There are blood vessels inside of us that are so narrow that when a single red blood cell tries to squeeze through, that blood vessel ruptures, causing internal bleeding. Internal bleeding can be fatal. However, our bodies do produce a defense against this, and really any type of bleeding, and that is the enzyme named thrombin. I like to think of thrombin as this superhero plumber that circulates in our blood. And whenever thrombin comes across a damaged blood vessel, it grabs other molecules from the blood, stuffs them in its mouth, and then uses that to plug the hole. However, thrombin is really good at its job. And once it starts creating blood clot, even though thrombin does have other important functions, it really doesn't know when to stop. And if that blood clot gets so big that it actually blocks the blood vessel, it can create a thrombosis. A thrombosis is more common than you'd think, and it can kill you. This is particularly concerning in the field of medicine, because surgeons who make cuts and nurses that give injections are damaging blood vessels in the process. The current class of thrombin inhibitors that could be used to prevent a thrombosis from happening are actually pretty harmful to a patient. They essentially destroy a patient's entire thrombin supply. Well, the results of my research may actually offer a safer solution. You see, thrombin has a sidekick named thrombomodulin. And thrombomodulin's function is to basically come along and say, yo, thrombin, chill out, okay, you did it. You stopped the leak. Now go do one of your other functions. You know, go home, see your kids. And even though we've known about the relationship between these two for over 30 years, we still don't know exactly how this message is communicated. The explanation that my research works on is that thrombomodulin actually changes the way that thrombin jiggles. You can think of enzymes like thrombin as these jiggly little molecular hairballs. The method that my research uses places a small probe in the solution around thrombin. And that probe gives off a signal that basically tells us how much the different regions of thrombin are jiggling. And what we see is that when thrombin is alone, it jiggles in one way. And when thrombin jiggles that way, it's able to grab onto those molecules and make the blood clot. However, when thrombomodulin is present, thrombin jiggles in a different way. And when it jiggles that way, it can't grab onto molecules in the same way, and it can't create the blood clot. In particular, there's this one region of thrombin that we see is stabilized when thrombomodulin is present. And when this region is stabilized, we see that in turn, the mouth of thrombin may actually be stabilized in a particular conformation or orientation that we think is really prime for switching thrombin's activity towards its other functions. Imagine, we could create a drug using this information that either enhances or mimics the effect of thrombomodulin on thrombin. This would not be dangerous to a patient at all because it's taking advantage of an already natural relationship. So doctors could give this to patients, prevent a thrombosis from happening, but not have to worry about causing any damage to a patient at all. And so really, in short, my research, studying this little plumber jiggle inside of us, may actually one day help doctors save lives. And so, right now I want to take a moment. Can we all give a round of applause for the little plumber inside of us that is keeping us alive? Thank you.
All right, thank you very much, Wiley. So this is a very engaged research that you're doing on the blood clot and the relation to thrombosis. Tell us a little bit about, what do you do in your free time?
Well, we live in beautiful San Diego, we get a lot of sunlight, so I try to go outside, do lots of activities out there. Love the beach. I like to rock climb as well.
Do you do any hiking, trailing?
Hiking, backpacking, camping.
What would be the favorite trail that you follow?
Oh man, well last summer I hiked the John Muir Trail, which was 19 days of backpacking,
Yeah.
14 days without showering.
Okay.
After 5 days, you don't get stinkier.
Don't tell me that you go back to the lab right after that.
I showered first.
All right. Thank you very much.
Thank you.
Yeah, thank you. All right. Our next finalist is my friend Latvia, yeah, Ivanovic. And he's from neuroscience, and he's going to talk about creating a monkey cocktail party.
Hello, everyone. My name is Vladimir Body. I'm here trying to talk to Oops.
Okay.
Why don't we just turn it down a little bit? All right, thank you. What you have all just experienced is something called the cocktail party effect. So named because it typically happens when you're chatting with a friend at a party and there are multiple distracting conversations going on around you that you need to actively ignore in order to hear your friend. Now, researching this effect can show us how we're able to actually process complex sounds and pay attention to things that we care about. And within human research, what we found is that there's two main processes to keep in mind. First is the acoustic pathway that takes in all the sounds from the ears and turns into an electrical signal. And then the attentional pathways from the front of the brain that help tease apart and pay attention to the specific voices or sounds you care about. Now, opportunities to record from within humans are few and far between, and so we need to look at animals with similar brain structures and behaviors as us, something we like to call an animal model. So enter the marmoset. The marmoset is a primate with a very similar brain structure to ours, as can be seen by these four colored areas that we have in common, which are necessary for vocal communication in both species. So my research is actually developing the marmoset as the animal model for cocktail party research by emulating key aspects of a cocktail party for monkeys. So, the common marmoset is a small vocal monkey from Brazil. It loves to talk back and forth ad nauseum with each other, much like some humans do in their own conversations. This makes them ideal candidates for animal models in vocal communication research. And so if I just take previously recorded conversations of these monkeys, play them in a room, I basically created a monkey cocktail party. And so this is diagrammed here with Robin, the subject, and Marion, the target. They're talking back and forth to each other while these distracting conversations are going on around them, talking about the latest grapes or egg whites that they had that day. And if you look at the precise timing of Robin's calls relative to Marion's and the distractors, we can actually quantify just how engaged the subject is with the target. This intuitive demonstration of the cocktail party effect has actually never been done before. So how did they do? Pretty darn great. Across 6 subjects, we have a consistently higher response for the targets and not the distractors. This means that they're able to ignore the distracting conversations and only engage with one monkey, much like we do within our own parties. So we have developed behavior, and we also have similar brain structures. We have a new animal model for the cocktail party effect, which means we can start recording from these monkeys at the cellular level within their brains while they're doing this task. So that one day, hopefully, we can explain how we're able to, hopefully we can explain how we're able to navigate the cacophony of modern life and, maybe give you something new to talk about at your next cocktail party. Okay, thank you.
Thank you. Yeah, this is a very, very good talk on the marmoset and your research on that, as well as how it's connected to the cocktail party effect. So tell us something about, you have been playing the boarding games. What are the, something about it? So.
I think I have my group right here that I played Dungeons & Dragons with, or Pathfinder, if anyone knows the difference, for the past 6 years. So we're skipping on that tonight so we can watch me perform here.
I see. Well, tell us something that beyond the game, that what else have you been doing? I know that you've been doing a lot of wonderful things.
Outside of Graduate Student Association, which every graduate student should, pay attention to and go to our events, I actually think the main thing that I actually like to do is work on actually making sheet music for music boxes. You can actually find programmable ones. So if you're willing to hole punch over 1,000 holes into a thin strip of paper, you can make stuff like Hurt by Johnny Cash. Very difficult to do. His cadence is not helpful in that regard.
Wow,
Yeah.
okay, that's wonderful. And what is your go-to comfort food and why?
I think my mom should be watching this right now. So there's something called Serbian pita. It's kind of like spanakopita, but you remove the disgusting spinach and just have the delicious cheese. Yeah, it's one of the best things ever, and basically almost every time I visit home, I come back with a giant tub full of that stuff to enjoy by myself, and sometimes I share with other people.
Thank you. Thank you. Tell us someone that will have major impact on your life.
Well, actually, I would say sophomore year of college, Dr. Simpson Rowe, we were talking about where I wanted to go to college, and she happened to come here for a postdoc for her, I believe, psychiatrist training. And she ended up just saying offhand, just like, just consider, UCSD. I think their neuroscience program is really nice. And here I am. So that's how it goes.
I believe she's right. Thank you. Thank you. Yeah, next finalist is Javier Clark, and theater and dance. Oh, Xavier. Yeah, Xavier Clark. Sorry about that. Yeah, the presentation is Intersectional Approach to Theatrical Storytelling.
Hi,
Start the act.
I'm Xavier Clark, and I'm an actor. These are currently America's most produced playwrights. They are all white, male, cisgendered, and straight. And therefore, the worlds that they create in their plays often do not include people who are part of marginalized groups. I do the research that I do because representation matters. When people cannot visualize themselves, their dreams are lost. When people who are not white cannot see themselves reflected in the arts, in the media, their dreams are lost. When all Americans can go to the theater and see themselves reflected on that stage, now that is something that dreams are made of. So how do we ensure that the stories that are told on the American theater stage actually reflect what America looks like today? Intersectionality. Now, intersectionality is the concept used to describe the ways in which systems of oppression are actually interconnected and cannot be examined separately from one another. Now, I implement these intersectional approaches in my storytelling as an actor in order to bring these specific stories to life. At UCSD, the first play that I worked on was Lorraine Hansberry's timeless classic, A Raisin in the Sun, which deals with the intersection of racism, the American dream, and capitalism. In Raisin in the Sun, I portrayed Joseph Asagai, who is a Nigerian college student. Now, in order to wear his character on my skin, my first step was to infuse his cadence as a Nigerian man into my speech patterns, which included watching timeless and long videos of Nigerian men speaking and then trying to wear that on my skin. The next play I worked on was Tambo Bones, which was a minstrel show with a contemporary twist on it. Now, Tambo Bones dealt with the intersection of racism, capitalism, and how we view black performance today. Now, my process and research for Tambo Bones included the theory-based research, which was about how intersectionality is infused in our daily lives, as well as the physical exploration of the character through an acting style called clowning, which involves a lot of audience interaction and a lot of large physical gestures. Now, those were my two processes that I worked on so far as part of my research, but I do the research that I do in hopes that these intersectional approaches will allow someone to see their lives reflected back to them, and so that they don't have to force themselves to see themselves in cisgendered, white, male, straight narratives in the American theater. Thank you.
Thank you, Xavier. So it looks like you have a lot of fun doing research on, on this topic of, and storytelling approach to the intersectionality.
Yeah.
So tell us something about, lists of, things that maybe just give me one item on your bucket list that wish you can do it.
It's not necessarily a fun thing on my bucket list, but I want to go to Liberia someday. So I'm half Liberian and half Turkish, and I've actually never gotten to see parts of my Liberian heritage, and so one of my bucket list items is to be able to go there and visit and see actually a big part of my heritage.
Ah, great. Yeah. Okay. What is the comfort food that you like to, and also why?
Oh, comfort food. So I'm gonna go with Shake Shack. I know we're in California, everyone's an In-N-Out fan, but go Shake Shack. I went to undergrad in New York, and Shake Shack is huge out there, and every day when I would have a bad day in school or stressful day, on my walk home, I would stop by the original Shake Shack, which is in Madison Square Park in New York City, and I would grab Shake Shack as a way to console myself after a long day. And after doing that for 4 years in undergrad, now it's become my comfort food. And thankfully, we have one in San Diego. We have a couple actually now. So yeah, Shake Shack is my comfort.
So when you are not under stress, what would you like to do with your free time?
Well, I don't have that here, so. But in the rare time that I do have it, I'm a coffee shop enthusiast. So I love exploring coffee shops around town, and I also love thrift stores. So thrift stores and coffee shops, I try to hunt them down when I have the rare free time.
Any recommendation nearby, the coffee shops that are?
Coffee shops, I love Communal Coffee. It's in North Park. They have a great honey lavender latte. If you're a latte fan, go check it out. That's definitely my favorite.
Thank you very much.
Yeah, thank you.
So next we'll have a student finalist, Joanna Wong from the Material Science and Engineering, talking about using color to fight infection.
How does nature make the colorful world around us, such as flowers, butterfly wings, or an abalone shell? The first thing that comes to your mind is probably a pigment or dye. While those are true, nature has a secret ingredient, and she uses structure to make color. Take a look at the abalone shell and at the transparent crystal. Nature made both out of the same material called calcium carbonate. But the reason the abalone shell looks so vibrant is because if you zoom in under a microscope, you'll see that it's made up of many thin layers. So that when the light around us reaches these thin layers, it bounces around in between, and only one color manages to escape and reach your eye. And because this color is due to structure alone, we call this structural color. So, if nature can make thin layers into colorful things, can we as scientists mimic nature's structure to also make vibrant materials? In my research, I focus on converting dull, boring-looking silicon, which is on the top right, into something beautiful and vibrant. I give the silicon structure by hollowing it out so that it looks like a sponge. And like the one you see in your kitchen, it's made up of dense and light layers. And because I can control the thickness and the spacing of these layers, I'm able to turn gray silicon into any color I want, as you can see from the picture. The most special thing about this structure is that it can get soaked in a liquid. And when this happens, the color changes. This is very important to us because it allows us to build sensors out of these sponges and to tackle real-world problems, such as catheter-related infections. Catheter-related infections affect over 80,000 Americans alone, leading to tens of thousands of deaths and up to $2.3 billion in hospital costs. One of the reasons this happens is because nurses don't know whether or not the catheters are sterilized. We help nurses visualize the sterilization process by embedding the silicone sponges onto the tip of catheters, so that when the nurses swab the catheter, it changes from green to red. This tells the nurse that they have applied the alcohol on the entire surface of the catheter. This also tells them that they need to stop and wait for the alcohol to dry. And once the alcohol is dry, the catheter returns to its green original color, letting the nurse know that it's time to go and inject the therapeutic. So by simply embedding nature's structure on the abalone shell into the tip of catheters, we can use color to fight infection. Thank you.
Thank you very much, Joanna. This is a very interesting presentation of your work on mimicking natures from layer structures, nanostructure, all the way to solving a surgical or medical problems.
Thank
you.
So
tell us something about what would be your favorite place to visit and why?
I would like to go to Florence. I've actually been there once, but I really like going there because they have really good food, especially pasta.
Pasta.
Yeah,
yes.
It's not like the American one. It's not greasy at all. It's really light and fresh.
Yeah. What else do you like at Florence?
I also really like their gelato. Yeah.
Yeah, that's very, very nice. And yeah, tell us someone who had major impact on your life so far.
So I would say my mom made a big impact in my life. I think growing up, I didn't play with like traditional girl toys like Barbies. I played with a lot of rocks and Legos, and she really encouraged that. And so I think that maybe encouraged me to do something like this now.
Okay, thank you very much.
Thank you.
Yeah, next we have Timothy Saul from Biological Sciences, and his presentation is taking out the trash.
Our bodies are made of 37 trillion cells. That's 37 trillion little units all working together to make us who we are. Since the discovery of the cell 400 years ago, biologists have worked to unravel its mysteries, which has led to countless advances in how we understand ourselves and modern medicine. Like those pioneering biologists, I want to understand every detail about how these little things work. We can think of cells kind of like a factory. They take nutrients in and create all the things that are necessary for our bodies to live. Also like a good factory, cells have a system to check the quality of everything they make. A factory has inspectors who looks over products, checks to make sure they meet certain specifications, and throws bad products in the garbage. Cells have to do something similar because if they were allowed to make bad products, those products could go on to harm our bodies. What I want to understand with my research is, who are the cells inspectors? How do they decide that something's bad? And how do they throw those bad things away? To tackle this, I give products to cells and see what they do with them. Here on this graph, we can see my data on how cells get rid of products over time. At the beginning, cells have 100% of the product that I give them, but over time, these curves go down, indicating that they're throwing it away. In gray, we can see what happens when I give cells a normal product. It sticks around, only getting thrown away very slowly as things wear out. In the solid blue line, we can see what happens when I give cells a bad product. They throw it away very quickly in order to protect the cell, as indicated by how sharply that line goes down. Using the system, I can ask questions about how cells take out the trash. For example, I would predict that if we have an important inspector and I remove it from cells, garbage should start piling up. I've been interested in a part of the cell, a protein called A1, which is sort of like an employee who definitely does something important, but no one's really sure what they do. Using modern biology techniques, I can remove A1 from cells and ask what happens to garbage. Here in the dotted line, we can see that when I remove A1, garbage hangs around for much longer. This evidence has led me to believe that A1 is responsible for removing specific types of garbage and represents the clearest picture we've ever had into how the system works. These quality inspections are vital for our health. Problems with the system have been shown to cause many diseases from cancer to Alzheimer's, where their cells pile up garbage that doesn't get thrown away by our inspectors. With what we've gained from my research, we may be able to find ways to teach those inspectors to throw those things away. However, before any patient can receive a breakthrough treatment, We have to have a basic understanding of the nuts and bolts of how this system works. We have to do the legwork of tearing apart the cellular factory in order to see how everything fits together. What I've dedicated myself to with my PhD research is laying a solid foundation of understanding, with the hope that future researchers will build on that foundation in order to cure the world's intractable diseases. Thank you.
Well, Timothy, sounds like your research is going to have major impact on personalized health.
Hopefully.
Yeah, tell us something about, that you have been doing a lot of work, but I look at your resume. So tell something that, most people don't know about you.
I think most people don't know that back in high school, I was in a rock band. We were called Livin' to Die because we were edgy teenagers. We were all super into the Saturday Night Live sketch with Christopher Walken and the cowbell. So I played the cowbell for them, and that's the extent of my musical talent, is that I can hit a cowbell and gyrate, I guess.
What did your parents say about your activity?
Oh, they're right here. They're always proud of me.
Yeah, that's wonderful. Yeah, and tell us one thing in your bucket list that you would like to do.
Oh yeah, one thing on my bucket list, I've always wanted to get a dog. And actually, in about 3 weeks' time, I'm going to get a dog. I'm super stoked. Very excited about it.
Okay, wonderful, wonderful.
Thank you so much.
So I hope you'll become an important inspector one day. Next, we have Keisuke Matsushita.
Yep, thank you.
Thank you, from Mechanical and Aerospace Engineering. What makes impact resistant wood impact resistant?
All right. So, natural materials are full of adaptations accumulated over millions of years that allow things like horns, hooves, and bone to absorb large amounts of shock safely, even though they're lightweight. At the lab I work at, we study these natural materials to try and come up with the next generation of bio-inspired composites for the US Air Force. I happen to specialize in wood. Why? Because we've used it in every tool imaginable since the dawn of time. Everything from clubs to the stocks of heavy machine guns. And across time and civilizations, the surprising thing is we've only used a few species, walnut, willow, maple, to name a few, without really understanding why. It's all just trial and error. So I wanted to know why. I got a big gun, and I started smashing a bunch of different wood to see which ones could absorb the most kinetic energy with the least mass and volume. But before we can understand what makes some wood better than others, we have to know what wood is. At the smallest length scale, wood is made out of long molecules called cellulose. These get wound up into hollow tubes called fibers, kind of like the grip tape of a tennis racket handle. Then you get a bunch of these fibers together arranged in parallel, and you start to see something that looks familiar from your high school biology textbook. At each of these length scales that I just described, you see big differences between how impact-resistant and non-impact resistant wood behaves. Starting at the top, in most wood species, when these individual fibers break, they kind of just snap off in half. But in impact-resistant species, these fibers that are wound up will actually unspool. They'll helically unwind, which means many bonds are being broken, which means more energy is absorbed per fiber. You can also see how groups of fibers behave differently. In most wood species, these fibers are over-adhered to one another, which means they don't have a lot of space to move around. So when a crack starts to go through them, it's instantaneous and they break apart. But in impact-resistant species, these fibers aren't actually that adhered to one another, so they can slide past one another, shearing and bending, which adds a lot more deformation that they can take before failure. It's another mechanism of impact resistance. Finally, with the naked eye, you can see that in most wood, the crack just goes right through the middle, like when you split a log. But in impact-resistant species, that doesn't happen because the fibers don't grow straight. They'll actually spiral around the trunk of the tree. And not only that, but the handedness of that spiral will alternate once every few years. We call that interlocking grain, and it basically forces the cracks going through the wood to take all these winding, crazy paths, which takes a lot more energy, which means more energy absorbed during impact. Combining all these tricks Impact-resistant trees can absorb over twice the amount of kinetic energy that other trees can at the same density, which means if we can use these tricks in the next generation of composites, we can get planes that are faster, stronger, lighter, and more fuel efficient. Thank you.
Thank you very much.
Oh, thank you.
Yeah, I learned a lot from your talk about
Thank you.
the resistance of the fibers in terms of impact resistance. So, this is actually in a field that I've been looking in.
Oh,
the
okay.
different fibers.
No hard questions, right? Just
No, it's a glass fiber, not the wood fiber, but I'm very fascinated with your work. So, well, tell us something about yourself. What's your dream vacation destination and why?
I'd really like to see the mountains in Yunnan province in China. That's the crazy ones that are in the Avatar movies, and I just really want to go there and like hike around and stuff, and eat the food.
Yeah, well, speaking of food, what is your favorite go-to comfort food and why?
So my heritage is Japanese, and I really like tinzara soba, which is basically buckwheat noodles with deep fried vegetables and seafood on the side. So you got your fried stuff and you got your carbs. So everyone likes that. That's universal.
Tell us someone who has impact on your life.
Yeah, he's right there.
Stand up?
Yeah. Okay, I'm sorry I made you stand up. That's one. We've been together for 8 years now, and yeah, every night we talk about our research at the dinner table, so I've had a little bit of practice, and yeah, you always make me a better person, so thank you.
Thank you very much. Thank you.
Oh, sorry.
Let's give a hand to all the 10 finalists. And now we have to leave the panel of judges to do their hard work and deliberate. And we have a couple minutes here.
Yeah. So the judges are going to come and go to a different room, and we're going to meet back here at 6:20, so in about 15 minutes. So the audience is welcome to mingle, and the judges will return, and then we'll have the results and an award ceremony. So we hope you'll join us at 6:20.
So first, I would like to invite student finalists to come to the stage in alphabetical order. So first is Pauline Chung. And Javier Clark. Vladimir. Thank you. Brianna. Keisuke. Thank you. Angela Nicholson. Riley Peacock. All right. Emily Piers. Timothy Shaw. Joanna Wang.
All right, who's ready to hear one more? Yes, one more round of applause for our amazing graduate students. All right, so the second runner-up, third place, is Emily Pierce. And I picture. No, picture. And the first runner-up in second place is Joanna Wong. And our campus champion, UC San Diego campus champion for 2019 Grad Slam is Angela Nicholson. The judges had an incredibly hard decision to make. That's why it took us so long. Apologies. But thank you again to everyone for participating. Congratulations to all of you, and especially to Angela, campus champion. We look forward to... And now we invite everyone to mix and mingle, enjoy some refreshments, and have a little bit of time for networking and getting to know our amazing graduate students who are both on stage and out in the audience. So thank you all for being here.